How does the brain compute? Can we understand the neural dynamics by analyzing neural signals? Suppose you're given a time-varying one-dimensional motion stimulus, and you need to report the direction of the total motion. Mathematically, this is an extremely simple computation, a temporal integration of motion strength over time, which is then compared to a threshold. However, how does the biological neural system make such a decision? For this perceptual decision-making example, there are a few proposed theoretical models of neural computation. Suppose this ball represents the current neural state, and the two values represent the two possible decisions. If the stimulus pushes the neural state around, left and right, proportional to the motion strength, the ball will bounce around and roll down to an eventual decision. But there are many other ways to perform approximate integration. We can use a set of discrete intermediate stable states, or a continuous attractor where any intermediate state is stable. We can draw the vector field that represents the dynamics which dictates how neural trajectories evolve over time in this neural state space, and we can expand this to multiple dimensions. So, how do we connect these theoretical models of neural computation to the actual neural data? First, we can extract low-dimensional, single-trial neural trajectories from simultaneously recorded neural signals using methods such as GPFA, PLDS, or VLGP. Then, we need a flexible model of the dynamical law that can capture various features proposed in theoretical neuroscience. Specifically, we need a time series model that can capture fixed points, bifurcation, oscillation, chaos, and continuous attractors, all of which can be elegantly described by the language of continuous dynamical systems. In this work, we propose a simple time series model which looks similar to the widely used NARCS model, but there are 4 key differences which make it more suitable for the interpretation of neural dynamics in the context of computation. First, we directly model the vector field, which represents a small change for each time step. Second, the change is modeled to be locally smooth, which we achieve by using a radial basis function network to approximate the vector field. Third, we have a contractual term that promotes a global contraction towards the origin. This helps the model focus on fitting regions that are densely sampled by the trajectories and avoid unfounded extrapolations that can result in misleading interpretations. Finally, we assume that the input interacts with the current state through a locally linear operator. We fit this model by optimizing mean squared error using stochastic gradient descent, and we demonstrate that this model is flexible enough to capture key dynamic features of neural computation. One example we show is the ring attractor for internal representation of circular variables, such as head direction. In polar coordinate, we can describe it as attraction towards a fixed radius and integrating input in the tangent direction. The training set consists of 150 random initial conditions with white noise input. The trained model recovers the continuous attractor as a set of fixed points populated around the ring and predicts the input-driven integration well. For other examples and more details, please check out our NIPS 2016 paper.